Okay. So one of you sent me a message requesting me to record the lectures. This is not a substitute of in-person lecture. And in fact, as you will find out, I'm not very good at posting a video on the campus. So the posting can be delayed. And so I do recommend you to come in person if you can. But I think some students requested this for review purpose, which is okay for me. So I'll try to record the lectures and post that too. So thank you for the Hagoromo talk. This is very helpful. So I think the purpose of today's lecture is to explain why you get 26 dimension for bosonic string theory. And we'll see that there is analogous condition for superstring too, which gives rise to D equal 10. And so this is one of the interesting features of string theory, that the dimension in which the theory is consistent is fixed. So this is unusual for physical theory. For example, if you look at Maxwell's theory or Newton's equation of motion, you can write it down in any dimension. The behavior of the theories are different. For example, the stability of planetary motion can depend on dimensions. And so the physical consequences are very much dependent on the dimension you define the theory, but you can formulate a theory in any dimension. And that's not the case in string theory. So for example, in bosonic string that we are looking at, consistency requires D equal 26. And so there are a couple of ways to explain why this has to be the case. And I'll explain one of them today. And the other one will come in a couple of lectures. And it's one important feature of string theory, so it's good to understand it thoroughly. And it's good that the D is resulting D is greater than 4, because 4 is where we live. So for example, in the case of 10 superstring, the consistency requires D equal 10. And so we have to do something about 6 extra dimensions. And it turns out that this geometric feature of this extra 6 dimensions is very restrictive. And it also carries a lot of interesting information about physics in 4 dimensions. So we'll see that later. But let's continue the discussion of first quantization of strings and try to get to D equal 26, okay? And so we started out with Nambu-Goto action. So this is much better. Okay, and so the action is 1/2 pi alpha prime minus 1 two-dimensional integral of induced metric. And the induced metric is given by this, where del A refers to the derivative on the worldsheet coordinate. Okay, and so what we observed is that this is a constrained system. That this action is invariant under reparameterization of two-dimensional coordinates, and this gives rise to constraint. And one way to see the constraint is to find the momentum conjugate to the coordinate, and it's given by this. If you do the calculation, oh, I was using alpha beta. Maybe C. Oh yeah, so this is the type. I was using A and B and alpha and beta. So I try to be consistent. Okay, and then you find that there are two constraints, and that can be combined into the condition that P mu P, well, we can write it in this way, P mu plus minus 2 pi alpha prime del 1 of x mu square is equal to 0. So there are two sets of conditions. And this should apply for everywhere on the worksheet. And so this is called Virasoro constraint. Named after Miguel Virasoro, who first pointed out this condition is required. Okay. So this condition is very closely tied to the fact that this action is invariant under arbitrary coordinate transformation. The sigma A goes to sigma A prime is F A of sigma. And so if you have this type of diffeomorphism or reparameterization invariance, so sigma are the parameters of the two-dimensional worksheet. So this is called reparameterization invariance or diffeomorphism invariance, coordinate invariance. There are various different ways of saying it. But using that, we can choose sigmas, coordinate sigmas, such that the metric is diagonalized. Where this is a diagonal metric. I'm assuming the metric is the Lorentzian on the worksheet, so it's like that. Where lambda is some number. Well, in general, it can be a function of the position, sigma. Some positive function. The reason is that, well, we have two reparameterization functions that we can choose. And metric G hat AB, this is the induced metric, has three independent components because this is 2 by 2 symmetric matrix. Can you read this bottom part of the blackboard, or do you have difficulty with that? Are you okay? So therefore, by doing reparameterization, we can actually at least eliminate two components. So what I have done is to use this freedom to choose so that the off-diagonal element is 0 and the diagonal element has the same magnitude with opposite sign. So we can impose this condition by using coordinate invariance. Okay, and this is not fixed. This is still unfixed, but in fact, this does not show up in the action as we will see. Okay, so suppose I choose this coordinate. So this is called a conformal gauge. So I'm using the language of gauge theory. So reparameterization invariance you can think of as a kind of gauge invariance on the two-dimensional worksheet. So we call that as gauge symmetry. We regard that as a gauge symmetry. So you can think of this. So we are choosing the condition so that the metric takes this diagonal form. And this is called the conformal gauge. Okay. This is called the conformal gauge. And in the conformal gauge, the relation between P and X gets simplified because the determinant of G is now lambda square and off diagonal element is 0. So that means that it only has 0 component, which is lambda. So, and this is inverse. So this and this get canceled. So this means that actually P mu is 1/2 pi alpha prime of del 0 of X mu. And yeah, so this will be the condition. And so in this coordinate, in this choice, this Virasoro constraint, now became these conditions. So you have this set of conditions. So this gets simplified in this way, and it's become easier to solve. Okay. So now, so we fix the gauge, but as is often the case, so you might have seen it in quantum electrodynamics, for example, or Maxwell theory, that even if you fix a gauge, sometimes you have a residual gauge symmetry. So you may have a residual gauge symmetry. So let me, for example, give you an example. So suppose you have a Maxwell theory. So in the Maxwell theory, the field strength is del mu a nu minus del mu a mu. And the equation of motion can be written in this way. So this is, you might have seen it in electron EM class. And this theory, this equation of motion has a gauge symmetry of a mu goes to a mu plus del mu of lambda, where lambda is some function in space time. So this is the gauge symmetry. So sometimes having this symmetry is inconvenient because solution to equation motion is not unique. And also, if you want to quantize the Maxwell theory, then you need to fix this symmetry. You need to find some appropriate slice to find physical solution independent of this symmetry. And so there are a variety of conditions we can consider imposing to fix this symmetry, that to make the configuration of A to be not invariant and to not to have this degrees of freedom anymore. So one way is Lorentz gauge, which is this equation. It's called Lorentz gauge. Okay, so this fixed the condition, but this does not completely fix it, because under this, so we can see how this condition changes under gauge transformation. Where if you do this gauge transformation, then this condition changes to be the box of lambda. So if you impose a condition that divergence of A to be 0, then under gauge transformation it becomes like this. So this condition is invariant under this gauge transformation, not for arbitrary lambda, but for lambda satisfying the D'Alembert equation. Okay, so this is called the residual gauge symmetry of the Lorentz condition, Lorentz gauge condition of the Maxwell theory. So there is an analogous residual gauge symmetry in this case. There is an analogous residual gauge symmetry in this case. So, so what kind of gauge symmetry remains invariant? What kind of reparametrization preserves this condition? Well, so one way to see it is to note that if you have this metric, then diagonal form of the metric, then the metric takes this form. Okay, and so we can write this as lambda. Do I have lambda? Yes, lambda times minus d sigma 0 square plus d sigma 1 square. But you can also write it as lambda. Let's see the note. I just want to make sure the notation is correct. Minus lambda times d sigma plus d sigma minus, where where sigma plus minus is defined to be sigma 0 plus minus sigma 1. Okay, so this is sort of 45-degree angle coordinates. I think this is sigma 0 and this is sigma 1. Then we have color chart. No, we don't have color chart. So we can have this type of coordinate where, so let me make sure. So where, where here sigma minus is constant, where this is sigma plus is constant, right? And so these are called the light cone coordinate. These are called the light cone coordinate. These are called light cone coordinate because if this was so in this two-dimensional space, if you look at the propagation of light, the light, so here I'm using natural units, so the speed of light is 1. So the light travel in this 45 degrees. So these coordinates are along the trajectory of the light. So these are called the light cone coordinates. The light cone in 2 dimensions is like these two 45 degree line. So in this light cone coordinate, the metric takes this kind of totally off diagonal form. So from this, you can immediately see that there is still some kind of reparameterization symmetry that preserves this form of the metric. Can you guess? Well, if I choose sigma prime plus to be some arbitrary function of sigma plus, then the sigma prime plus is equal to the derivative of f with respect to sigma. And similarly, if I choose this to be some arbitrary function, then d sigma prime minus is equal to g prime or h, because g is confusing with metric. Let me choose h like that, right? So then we see that under this coordinate transformation, the metric can be expressed, the same metric can be expressed as the 1 over f prime h prime of minus lambda of d sigma prime plus d sigma prime minus. So the same kind of form. This form of the metric is preserved. This diagonal form of the metric is preserved. So you can think of this as the residual symmetry. Okay. So what am I getting at? Well, so we started out with this Nambu-Goto action, and then we chose the case where GAB hat is diagonal. And then there is a residual symmetry. So this is the conformal case. And then there is a residual symmetry of transforming this into this. Okay, and you have whenever you have a symmetry, it makes group, and the infinitesimal transformation of group makes Lie algebra. So you might have learned it in your undergraduate course of mathematical method in physics. So this residual symmetry makes very interesting, very the symmetry. This residual gauge symmetry makes very interesting group, and it actually structure controls much of the dynamics of string theory. So we can look at the infinitesimal. So we can consider. So this. Oh, by the way, so this transformation is called the conformal transformation. So it's called conformal group. That the set of coordinate transformation that preserves this structure of the metric. Okay. So very interesting thing about this. So here we are considering the worldsheet to be 2-dimensional, and the conformal group in 2 dimensions is very different from conformal group in higher dimension. So in general, in D dimension, space-time, the group, the conformal group, actually, so Minkowski, the conformal group, namely the group of coordinate transformation which preserves the Minkowski metric up to multiplication of some arbitrary positive function, is SO 2, D. What does that mean? Well, we know what SOD is, right? It is a D by D matrix, space of D by D real matrix, which is orthogonal. So any element of this is so M is real, and M transpose M is equal to 1, and the determinant is 1. Is the definition of this is D-dimensional rotation group. So so this is similar to D-dimensional rotation group, except that now we have this funny metric 2, D metric, which means that if you have an element of M, then element M, then M transpose -1, -1, 1, blah, 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 1. So there are D of them, and M is equal to the same matrix. Okay. So this is a known fact about the conformal group in D dimension. If you try to find a conformal transformation that preserves D-dimensional Minkowski metric up to overall scale, then it makes group like this. So this contains, of course, this contains a subgroup SO1, D-1, which is a D-dimensional Lorentz symmetry. So this is a Lorentz symmetry. Right? So this is a known fact, but this is for D greater than 3. So D greater than 3, the conformal group is finite dimensional, and it is this group. But for D equal to 2, which is what we are considering here. Well, actually, so I was using D to be the dimension of target space, so maybe I should use small d. For D equal to 2, the conformal group is infinite dimensional. Is there any question? Okay. The conformal group is infinite dimensional because F and H are arbitrary functions. F and H are arbitrary functions. So you can, for example, do the following things. So suppose, for example, consider the situation where you have this two-dimensional closed string. The closed string, this one-dimensional, but it propagates like that. So let's choose the time coordinate on the worldsheet to be sigma going in this direction. So it goes from some minus infinity to plus infinity. And there is this space coordinate sigma 1, which is periodic. So let's choose the period to be 2 pi. Say, for example, sigma 1 plus 2 pi. So that if you go around 2 pi, it comes back to the same point. So then F and sigma should be should respect this periodicity. So let's write, for example, sigma prime plus to be equal to sigma plus something infinitesimal. And then sigma prime minus to be sigma minus plus something infinitesimal. Yeah? So then, in order to have this periodicity, this sigma plus and sigma minus has to be periodic function. So that means that the sigma plus minus, we can expand this as some e to the I n sigma plus minus. Right, so we can expand it in this way. And then what we can ask, what is the algebra of this conformal symmetry? Well, so if so this is infinitesimal transformation. So the transformation by sigma generates the derivative. So if you have some arbitrary function of f of sigma plus and sigma minus, for example, then under this transformation, we have a derivative operator acting on it. So this will generate this type of transformation, right? And so if you have two different sigmas, where two different set of epsilon, then that makes an algebra. Okay, so so what kind of algebra does it make? Well, so we have del plus sigma plus del sigma plus, which is summation n of epsilon n e to the I n sigma plus del sigma plus. So this actually makes an algebra. We can calculate the commutator. So we calculate the commutator of this algebra. You see that this acts on here, this acts on here. And so this makes the I times the m minus n of e to the I n plus n sigma del sigma plus. Okay, so this is the algebra of this structure is called the Virasoro algebra. The algebra of this type of structure is called the Virasoro algebra. So Virasoro algebra is algebra of infinitesimal conformal transformation. So if Ln is a generator for sigma prime, sigma plus goes to sigma plus epsilon n e to the I n sigma plus, where epsilon n is infinitesimal. Then essentially Ln is like minus I times e to the I n sigma plus del sigma plus. I have I here to make this to be Hermitian. And then this means that this Ln satisfies this algebra. Okay. So this is the classical version of Virasoro algebra. We haven't yet quantized the system. So the algebra we are getting is a classical version of the algebra. So this is a classical Virasoro algebra. So it's named after Miguel Virasoro because he organized the residual symmetry of this bosonic string in terms of this algebra and found a way to organize physical spectrum, as I will explain later. Okay. Okay, so you have this residual symmetry, which is whose infinitesimal version is expressed as the Virasoro algebra. So this is very different from higher dimensional case. In higher dimensional case, conformal symmetry is finite dimensional. In two-dimensional case, it's infinite dimensional. So that means that two-dimensional conformal field theory is more constrained. And this leads to lots of interesting development. We know much more about conformal field theory in two dimensions. Conformal field theory, which is the quantum field theory with conformal invariance, as we'll see, appears in string theory as a description of worldsheet dynamics of string theory, but it appears in many other situations, like, for example, critical phenomena in condensed matter physics, often, especially if it is second order phase transition, described in terms of conformal field theory. So in 2 dimensions, since we have this infinite dimensional symmetry, so we have a very sort of powerful result. For example, in certain situation, we can completely classify conformal field theory. In higher dimension, much less is known, although there have in the last 10 years or so, there have been significant development that Professor David Simons-Duffin in your department is one of the leaders in studying conformal field theory in higher dimension. So we have this residual symmetry. So we started out with Nabu-Goto action, and we imposed the gauge condition, conformal gauge condition, which is that G hat AB is equal to lambda times -1 plus 1, 0, 0. So we have this conformal gauge condition, but there is a residual gauge symmetry. Which allows us to transform sigma to the arbitrary function. So in order to find the complete physical spectrum, we need to fix this symmetry. And so one way of doing it, there are a variety of ways of doing it, but one way of doing it is to called light cone gauge. And so let me explain that. Okay, so let's so first maybe I should first write down the number action again. So we have this action, and then so from that we can deduce 2 things. One is the constraint between momentum and coordinate, which in the in the conformal case, the constraints were sigma 0 x, sigma 1 x is equal to 0. This is a contraction of space-time indices here, and then del 0 x squared plus del 1 x squared is equal to 1. So these are constraints, and the equation of motion, which you can derive by taking variation of this action with respect to x and imposing this gauge constraint, becomes just a massless Klein-Gordon equation in 2 dimensions. So in conformal gauge, everything is linearized, so it's nice and simple. So you know that in 2 dimension, solution to this Klein-Gordon equation has a very simple form. And so many things get simplified in 2 dimensions, and one of which is this fact that we can actually simply write down solution to equation. Well, in any dimension, of course, solution to linear Klein-Gordon equation is simple, but in 2 dimensions, it's especially simple because of the fact that this operator can be factorized. Okay, so essentially you can write, so this means that this is 4. Interesting. So so this blackboard defeat hygrometry. You have to, it's too smooth. The surface is too smooth. So the chalk does not get stuck. So you can actually write this as a product of the differential operator. Okay, so then if you have this, you can easily solve this equation because suppose you have this equation acting on some arbitrary function, let's say g of sigma 0, sigma 1. Okay, so how do you solve this? Well, we can write this as 4 times del minus del plus of g, right? So, so that means that del minus of del plus of g is equal to 0. So that means that del plus of g should not depend on the sigma minus. That this is what it means. So that means that so let me transcribe it. So the triangle equation can be written in this way. So this means that there is some function h, so that it only depends on plus. Because if you take derivative with respect minus, it's function. But then we see that we can then integrate this to write g plus to be g to be, we can integrate both sides and write this as g sigma plus. But when you do that, you have integration constant. And integration constant can be function of a sigma minus, because if you have a function sigma minus, it gets annihilated by it. So that means that you can have some another function like that. So that means that any solution to triangle equation, Maxwell's triangle equation in 2 dimensions can be written as some function of sigma and some function of okay, so remind you that this is the sigma 1 coordinate, sigma 0 coordinate, and then right one coordinates are like that. And so let's see. So this is the sigma minus constant, and this is the sigma plus constant. Okay. So for this reason, this is often called as right mover, and this is called the left mover. Different people have different convention, but I think this is logical to call this component as a left mover and this component to be right mover. And the reason is that suppose you think of this as some kind of wave equation. So in 2 dimensions, you have wave equation satisfying this, and then suppose we have this kind of initial condition where you have some kind of hump of weight. Okay, so this is vertical axis is g. And then there is this spatial variation like that. And now, if this hump is on this side, then that, because sigma minus sigma plus is constant, so that means that the hump moves to the left, right? If this is so the wave shape character described by V moves to the left, and the wave shape parameterized by W move to the right. So that's why it's called the left mover and the right mover. So what I wanted to say with this is that because the equation of motion for the coordinate x, which is remember sigma was a map from this. So what we are considering is a propagation of string in space-time in d dimension, which will turn out to be 26. And we are describing this as a map from 2-dimensional cylinder to space-time. And it turns out that that map satisfies this 2-dimensional wave equation. But because it's 2-dimensional massless wave equation, we can decompose it into left mover and the right mover. And so therefore, we can write this x mu satisfying this equation as x left mu of sigma plus and x right mu of sigma minus. I'm writing this as left mover and right mover. Okay, and okay, so any solution to equation motion takes this form. So we can take advantage of this to impose one more condition, and it is the right form condition, gauge condition. So, so right form gauge condition makes use of residual gauge transformation to choose a condition that x plus, which is x0 plus x1. So this is now right form coordinate in the target space. To be alpha prime p plus times sigma naught. Okay, this is a funny choice. And the reason that I use this notation is that remember that P mu in the conformal gauge is T2 pi alpha prime over 1. So in particular, P plus is equal to, sorry, P mu is equal to 0 of x mu. So in particular, P plus is this. So if you impose this condition, then it becomes 1 over 2 pi over P plus. And so the momentum density becomes P plus over 2 pi. So you can identify this P plus as total momentum in plus direction for the string propagating in this space time. Okay, so this is called right form gauge condition. So we can use this gauge, this to fix this degree of freedom. Okay, so we can utilize this degree of freedom to impose this condition. And if you use this, then x plus degrees of freedom is totally fixed. But not only that, x minus degrees of freedom is also fixed, because if you use this and substitute that into this constraint equation, then you can find, so this is one condition, but another condition is that this right form condition, del z x, del 1 x is equal to 0, and del 0 x squared plus del 1 x squared is equal to 0, combined with this condition, imposes that plus minus of x minus is equal to alpha prime p plus summation I is equal to 2 to d of del plus minus xi, del plus minus xi. So what this means is that both plus coordinate and minus coordinate are totally fixed by the gauge conditions. So only degrees of freedom on the worksheet are now in the other direction. So what I wrote it over there, but let me rewrite it here. So what we did is start with the conformal gauge condition, where we impose the induced metric to be diagonal. But then we impose additional condition called the right form gauge condition, where x plus is fixed to be alpha prime p plus of sigma 0. But then it's also implied that the minus is given by 1 over p plus alpha times I is equal to 1 to d minus 2, also 2, sorry, 2 to d of del plus minus xi squared. So what they did so remember that x plus minus is x0 plus minus x1, but there are other coordinates, right? So there is this x2, x3, xd. So these remains arbitrary. So these remains arbitrary, but these were fixed. So these are fixed. So if you choose this to be arbitrary solution to this wave equation, then with respect to that, these are fixed by this condition. Okay, to be precise, this is just the derivative operator. So this is fixed up to our constant, but that will be a center of mass of the string worksheet. Okay.
Now the worksheet is three-dimensional.
Well, so this worksheet is two-dimensional. Space-time is this. So let me try to explain the physical interpretation of what we did. Okay. So what we did is the following. So we have this two-dimensional string propagating in d-dimensional space-time. Okay. Now I cannot. The d is eventually going to be 26, so I cannot put that into my brain. But let's first project that into two-dimensional direction. So let's first project that into x1 and x0 direction, and then there is this d minus one-dimensional direction transverse to this blackboard. So these are called the transverse directions. And these are like right one direction. And so let's look at this right one direction first, x1 and x0, okay? And so now x minus, so x plus.
Should you write a d plus one-dimensional space-time?
No, I'm using d to be space-time dimension. That was the definition I gave at the beginning.
Here is x0, x1 to x.
Oh, excuse me. So yeah, so you are quite right. I might have made a mistake. Yes, I think you are quite right. The d should have been d minus one. So I think this is d minus. And then I think the error was over here. So this is d minus one. Excuse me. Thank you. So I'm choosing space-time dimension to be capital D for in this case. So this is d-dimensional space-time. Excuse me. And so let me try to make sure that x plus. Yeah, that's correct. So now, so the right cone direction. So this is x plus fixed, right? So if x plus is fixed, x plus is the sum of the two. So it's in this direction. So if you think of, so what is this? So in the right cone gauge, the time direction is sigma, worksheet time direction is x plus. So this is like you cut this worksheet, you slice the worksheet in this way. So each slice is like a circle. So I define, so once you have a propagation of string or in space-time, then I use x plus coordinate in the target space as a coordinate on the worksheet. Okay. And once then you use sigma, so this fixed sigma 0, and then the other coordinate, the other direction, are fixed by the constraint. The Virasoro constraint fixes the other direction. So this fixes the space, the worksheet coordinate completely. So reparameterization invariance is fixed in this direction. So this x plus and x minus directions are totally fixed. And so these are the only possibilities. And this is a way to properly describe the propagation and oscillation of strings. So for example, you can have the following situation. suppose we have a string propagating in this direction, and it might oscillate like that. And you want to see how string is oscillating. Okay? But if you are not careful, you might be misled to think that there is an oscillation of string worksheet when there is not. Because, for example, suppose you have a cylinder like that, which is straight, and any reasonable person would think this string is not oscillating. But for example, you can choose if there is a reparameterization invariance, then you can think, well, it's actually oscillating because if you choose worksheet coordinate like that. So suppose this is the sigma zero constant surface. Then suppose string is that we choose a coordinate so that it's sort of wavy in the sigma zero direction. Then it looks like it's actually with respect to that string looks like it's oscillating. But physically, it is equivalent to the straight worksheet. So you can think of this as a sort of fake oscillation. And so you want to remove this kind of misunderstanding. Right? So on the other hand, if it is oscillating in this kind of a transverse direction, then it's actually genuine oscillation. So fixing the worksheet residual invariance removes this kind of ambiguity. And after removing this ambiguity, the only genuine excitation is in this transverse direction transverse to the worksheet of string. Okay, so therefore, excitation actually happens only in this kind of d-1 dimensional. So oscillation, physical oscillations, you can say, are in d-2 directions. So this is important. Okay.
Sorry, can you repeat the reason why the oscillation in sigma one direction is not physical? Because there are conformal reasonabilities.
Well, so you can, so the reason is that if you reparameterize sigmas, then you can actually interpret oscillation in a sort of different ways.
Oh.
So for example, here I gave you a simple example where suppose you have a completely sort of static solid cylinder in this way. So look like there is no oscillation. But so for example, if I use this type of coordinate, look like there is no oscillation taking place. But you can choose to use wavy coordinate like that. Then it looks like it's oscillating, right? And so it doesn't make sense that the same physical embedding of the worksheet describe both oscillating situation and non-oscillating situation. And the reason for that is that there is arbitrariness in parameterizing these two dimensions. And so one way to do that is to remove that by totally fixing this arbitrary reparameterization. And after doing that, there are only d-1, d-2 dimensional direction of oscillation. Okay. Okay. Okay, so this is a classical theory. We have not quantized the two-dimensional worksheet yet. So that's what I'm going to do. And I hope I'll get to D-core 26 by the end of this lecture today, but we'll see. Yes?
Essentially, this means the embedding to three-dimensional surface can be arbitrary. Essentially, the worksheet itself is specified with the string and also its content. But all the other directions are arbitrary. Does that mean the embedding is arbitrary or?
So let's see. So suppose you have an embedding. So propagation of string in the space-time is described by this map, right? So it's a map. And so this map is well defined, and so the image is well defined object. So there is a well defined image. It's a mathematically well defined thing. What image of this is totally well defined. So suppose I choose sigma to be, say, for example, minus t, t1 to t2, for example, and sigma 1 to be 0 to pi, and periodic. So suppose this direction is periodic.
Essentially,
Yeah, can I complete?
Yes.
So then it's a cylinder, right? It's a cylinder, right? And this is where I'm embedding this cylinder into space-time. So the image is well defined. So this is the image. So if this is a map X, then the image of the map X is well-defined thing. What is not fixed yet, what was not fixed at the beginning was how to parameterize this thing.
Okay.
How to parameterize this thing was not fixed. And I said that what I meant was that this Nambu Goto action that we are using for this worksheet has this ambiguity on how to parameterize it, because the gauge invariant, the reparameterization invariant. So you can parameterize this thing in any ways. You can parameterize time and worksheet time and space in this way, or you can parameterize worksheet and time in this way. You have lots of different ambiguities. And depending on how you parameterize it, you have a different interpretation of how this is oscillating. So when you say oscillating, I mean you have to fix which direction the time is flowing, which direction is the space on the worksheet. And depending on how you do that, you seem to get a different picture of how string is oscillating. That's what I'm saying. But if you have a way of constraining the choice of coordinate, then there is a unique description of what we mean by string to be oscillating. Does it make sense?
Yeah.
So it's the same image, but you can have a different interpretation depending on how you parameterize it.
So essentially only the map itself is, or you can use formal.
Image is well defined. The map is arbitrary, but arbitrariness comes from the reparameterization invariance over here.
So, and then the other T-1 group criminalized or trivial after the map is
Trivial, what do you mean?
it doesn't got the intrinsic dynamics of the origin.
Well, I don't know what it means, intrinsic or not. So there is just a D minus 2-dimensional transverse direction, which are physical. And there are, so you have D dimension. So so D is decomposed into 2 light cone direction, and then D minus 2 transverse direction. And then we regard this D minus 2 transverse directions to be the direction where physical excitation is taking place. You can create or remove arbitrarily the excitation, seemingly excited, sort of what seems like excitation in this light cone direction can be eliminated by choice of working point. Okay, good. Okay, so what I should do? Yeah. So we are in this light cone gauge, and in the conformal gauge. So in conformal gauge, let's see. How am I doing this time? Okay, so now we would like to quantize this. So I'm going to do the first quantization. So maybe it's useful to discuss first quantization. Maybe it's useful to discuss what's called the Fourier coaction. So let me start with number Goto action first. So I started out with this action. Where is G hat? is del A x mu, del B x nu, eta mu. So, so this was where we started out with, but there is actually alternative description of same dynamics for the Polyakov function. Which is the following thing. So in the number-Goto action, the only degrees of freedom are x, which is a map from two-dimensional worldsheet to space-time. But in Polyakov action, you introduce worldsheet metric as independent degrees of freedom. So in the Polyakov action, so let me write this as number-Goto action, and this is the Polyakov action. In the Polyakov action, you have this metric, this action. That where now, so X is the map from the worldsheet to the target space. And then GAB is a worldsheet metric. And we regard GAB and X to be independent degrees of freedom in the Polyakov system. Okay, so in the number-Goto action, this induced metric is determined by this embedding map X. But in the Polyakov action, these two are treated as independent thing. But as you can see, so the metric enters into the action in a very simple form that it doesn't have any derivatives. And so you can actually algebraically eliminate. So you can actually show that by solving, if I solve this equation, and then substitute, if you solve this equation, then G is actually given by del A x mu, del B x nu, eta mu nu. Actually divided by square root of determinant of the same thing. So up to overall normalization, this is the same as this one, but this is the scaling invariant thing. Then actually I'm sorry. No, but I didn't write it correctly. So what I meant was that square root of minus G times GAB. I'm sorry, I missed it. I didn't write it correctly. Is equal to del A x mu, del B x mu, eta mu. So you can actually show that solution to this equation motion is of this form. Okay. Now, this fixes the metric up to rescaling. Because if you rescale this metric, this left-hand side becomes independent. So this does not fix this degree of freedom. But modulo this degrees of freedom, the metric is fixed. And this action is independent under rescaling. So if you substitute this into Polyakov action, so SP under this condition is actually S of number-Goto. So therefore, by removing this metric degrees of freedom by solving this equation motion, Polyakov action is equivalent to number-Goto action. So classically, therefore, we can use either number-Goto action or Polyakov action, and we can start from either one. Okay, and as we will see, quantum mechanically, these two are inequivalent. And one way to see D equals 26 appearing is that in D equals 26, these two descriptions are equivalent. And in other dimensions, they are not. And so that's one way to see it, but let me actually derive this fact. Okay, so what happens at the so let's try to quantize this in the appropriate way. So let's see. So where is my notes? Oh yeah, here it is. Okay, so I say that classically these two descriptions are the same, and if we choose Lightcon gauge, so if we choose conformal gauge, where the metric is diagonal, then the action, for example, if I choose Polyakov action, the 4 pi alpha prime, d square sigma square root of minus g GAB, del A x mu, del B x nu, eta mu nu, become 1 over pi over alpha prime of d square sigma, del plus x mu, del minus of x mu, where plus minus, as I defined, is sigma 0 plus minus sigma 1. Okay, and so so I say that this should satisfy the constraint. Which one?
Might be in the last line.
This one?
No. Yeah.
X. Oh yeah. Oh, this is X. Yeah, X. Yes, excuse me. Yes, you're right. Okay. So I say that there are constraints. So we can also write this equivalently as del plus x squared is equal to 0 and del minus x squared is equal to 0. And this condition can be interpreted as saying that energy, stress energy tensor of this two-dimensional theory vanishes. So stress energy tensor so this is something that I discussed in the first lecture when we discussed Weinberg-Witten theory. That any quantum field theory has stress energy tensor, which is the important ingredient of the theory. And one way to define stress energy tensor is to take variation of the action with respect to the method. Okay, so this is sort of a definition of the energy momentum tensor in quantum field theory. So if you have quantum field theory, and if you suppose you put the quantum field theory in any arbitrary curved space, if it's a local quantum field theory, You can do that. Then you can define stress energy tensor in this way. And this is a Noether current for energy and momentum. So if you have Lorentzian invariant quantum field theory, then the Noether theory says that the energy and momentum is conserved, and there is a current that generates energy momentum tensor, the energy and momentum, and that's stress energy tensor. Okay, so for this theory, for this two-dimensional theory, you can also define stress energy tensor. But it turns out that it has a special property because the SP, this Polyakov action, is invariant under rescaling of the metric. So if I rescale the metric in this way, then it is invariant. So that means that if you take variation of the metric in a way that scales it, then the action does not change. So what does it mean? Well, so this means that if I take variation of the action in this direction, it is invariant. But this is equal to GAV del S del GAV, right? And so this means, so this must be equal to 0. So what it means is that the TAB must be equal to 0. Because the stress energy tensor is defined as a variation of the metric, variation of the action with respect to the metric. So if you have conformally invariant system like this, that if you have a quantum field theory, in this case, this is a two-dimensional quantum field theory, which is invariant under rescaling of the metric, the energy momentum tensor is traceless. So if you have a conformal field theory, then has a traceless stress energy tensor. Okay, so that's what this means. So in two dimension, this stress energy tensor is symmetric 2x2 matrix. So you have 3 independent components. One of them is removed. You have 2 linearly independent components. So you have 2 components T plus plus, and it is actually related to these conditions. So by the conformal invariance, the trace part is there, but these remaining components of energy momentum tensor also vanishes by the constraint. So what it means is that the stress energy tensor for this system should be totally equal to 0 by combining both conformal invariance and the constraint, which is that this should be. Because after all, Weinberg-Witten theorem says that if you have a diffeomorphic invariant theory, then you shouldn't have energy momentum. And so we find that energy momentum tensor of this system is 0, consistent with what Weinberg-Witten theorem says. Okay. So now, suppose I go to the conformal gauge. So suppose I choose conformal gauge. So that this now becomes this action. So suppose, so let me remove P from the action. So this is the action we are considering. So this is now a very simple thing. That probably this is something you learn in the first hour of your introductory quantum field theory. This is a massless scalar theory in 2 dimensions. You have D massless scalar theory. So mu goes from 0 to D minus 1. So you have the D minus 1 massless free theory. And this is the energy momentum tensor. of the theory. And then we can find the canonical conjugation. We can perform canonical conjugation. What it does is to identify momentum conjugate to the coordinate x and impose canonical commutation relation. The momentum conjugate to x is derivative of x. So we see that there is a canonical commutation relation like that. Equal time commutation relation. Okay. And the sigma is a periodic coordinate. So since sigma y is a periodic coordinate, so we should be able to write this as in this way. We can do the Fourier transformation. We can expand this in this way, and we can rewrite this canonical commutation relation into commutation relation of these coefficients. Well, so I'm writing this rather quickly, but you can look up my lecture notes. So on Canvas, so you can review that. And if you substitute this into this commutation relation, then we find this set of commutation relations. So you have a bunch of harmonic oscillators. And then there is a Hermitistic condition. Okay, so these are the conditions. So now we can it is easy to see what the Hilbert space of this string theory is. So basically what you do is to start with a vacuum, which are narrated by all the alphas and alpha children. With n greater than or equal to 1. Because as you can see, alpha n and alpha minus n makes canonical conjugate pair. So they are harmonic oscillators. And so we can impose a condition that all the alpha with put plus n annihilate the vacuum. And then we can build the Hilbert space by acting these oscillators. And this ground state can have momentum. And so it can be either momentum eigenstate or position eigenstate. So it can be tensored with some function, which depends on x. But the x is the center of mass. So with this center of mass degrees of freedom and the excitations. So well, you can think of this as actually tensor. You can have tensor indices here and contract that with these indices. So I can write this explicitly. We can have mu1 to mu n, mu1 to mu n. Okay. So you see that, so this is the total Hilbert space of this string theory. And so you have infinitely many fields with lots of tensor indices in general, depending on which direction the string is excited. Okay. Okay, so that's what we should do. But so this is the total Hilbert space, but it's not yet physical because we need to impose a condition like that. So that means that we need to impose a condition that energy momentum tensor on this Hilbert space is there. So that's the condition we need to impose. Okay. So let's study the consequence of the condition. So for this purpose, it's useful to write this energy momentum tensor in terms of the oscillators. So let's first do that. So we now have Hilbert space. So let me summarize. So the Hilbert space of the first quantized theory consists of all these things. Acting on the vacuum tensor phi mu1 to mu(n), mu1 to mu(n) of x. Okay, so this is the Hilbert space, but this is not yet the physical Hilbert space because we have not imposed the constraint.
What is phi?
Phi is an arbitrary normalizable function on the space-time. So x is a coordinate in the space-time, right? Because we have, so what is the Hilbert space? Hilbert space is a representation of this algebra. So for example, there is this very important theorem in quantum mechanics called the Heisenberg theorem. You know Heisenberg theorem? Heisenberg theorem says that the unitary representation of this algebra is unique. And it is the unitary representation of this is given in terms of square integral function on this space. And so therefore this is represented in this way. And you can also easily see from what you learn in introductory quantum mechanics course that representation of this is also unique and is given by this harmonic oscillator. And so this is a unique Hilbert space realizing this argument. Okay, so that's what we work on. And but this is not yet physical because we have not imposed the physical state condition that we need to impose. And remember that the energy momentum tensor, so stress energy tensor, let's write plus component as T for simplicity. So this is a left moving component of the energy moment stress energy tensor, and it is this. And so it's useful to write this in the Fourier component. So we can write it in the Fourier component like this. And similarly, T bar, which is T minus component. Okay, and then we can see what the ln is. So if I just directly substitute this expansion into here, then you find that the ln is equal to m of 1/2 of alpha n minus m alpha n, and ln tilde is equal to summation m 1/2 of alpha n minus m alpha m tilde. Okay, so the task seems to be very simple. So what we need to do is now we have this quadratic combination of this harmonic oscillator. And we just need to find the space of solution to the condition that so you consider subspace of the Hilbert space which satisfies the condition that this annihilated. That sounds simple, except that there's one thing we need to care for, that is that this is sum, infinite sum over integers. This m goes from minus infinity to plus infinity. And for most of the n, it is fine. If n is non-zero, then this and this commute. So there is no ambiguity in defining this operator. But when n is zero, you have, so when n is zero, you have L0, which is summation over m minus 1/2 of L n alpha minus n. So then there is an ambiguity of whether these two operators don't commute with each other. That this, according to this commutation relation, is equal to n of eta mu nu. So they don't commute. So classically, it doesn't matter because the classical number commute. But quantum mechanically, they don't commute with each other. So we need to specify how do we place it. And after you do that, we need to solve this equation. And so because we are talking about infinite dimensional space, so there is some subtlety. And eventually we'll see that that is related to the fact that we get 26 dimension. Okay, so that will be what we'll discuss in the next lecture. Okay, so thank you very much. So I understand that next Monday is Institute holiday, is that correct? So that means that next lecture is on Wednesday. Okay, thank you very much.